yesterday's lecture was about doing uniqueness for the heat equation. So that's what's written up here. We did the one-dimensional heat equation. We looked at two different boundary conditions for that. We had Dirichlet conditions and Neumann conditions. And the case of the mixed conditions is something that I'd like you to try yourselves in the problem sets. Okay, but those are the three main classes of conditions that you need to cover. And you need to be ready to prove uniqueness for essentially the heat equation and the wave equation. Okay. Now in the notes, there's actually three classes of problems that you're asked to learn about. The third one being Poissons equation, which is essentially Laplace's equation. It's Laplace's equation with a right-hand side term. This, I'd like to double check over the weekend, but I'm fairly sure that you're not going to have to know this. Okay, so for now, until said otherwise, let's assume that I'd like you to know the uniqueness properties, how to prove uniqueness for the wave equation and for the heat equation. Okay. We're going to do it in the lectures in one dimension, as we did. Thursday, we did the one-dimensional proof of the heat equation. And in the problem set that you'll see in problem set number 10 is being done for 3D, for general dimensions, or 2D or 3D. But the idea, the approach, the methodology is essentially the same. The only difference is that when you work in 3D or you work in higher dimensions, you have to be working with volume integrals or surface integrals rather than just single one-dimensional integrals. That's the main difference. Okay? Good. So the question, is the math and music examinable if there are no problem sheets? It is examinable. Sorry, so someone said, oh, I think he said it wasn't. I don't think I said that it wasn't. It is examinable, but I'll make sure that in the study guide I try to explain the extent in which it might be examined. Okay. All right. So the objective today is for us to replace this with the wave equation. But to do the same type of boundary conditions. And again, the Dirichlet and the Neumann conditions will be treated virtually the same. It's a very minor modification if you use Dirichlet or Neumann conditions. And again, we won't be doing the mixed conditions. So let's replace this with the wave equation. And the difference with the wave equation is instead of a UT, we have a UTT. And instead of a kappa, we have a c squared uxx term. Instead of a single initial condition, you have an initial displacement and an initial velocity. So you have two initial conditions to worry about. You have a u of x0 equal to an f of x. And then you have a ut of x0 equal to a g of x. Okay. If you can't see this, this says ut of x0 equal to g of x. And again, we're going to be doing the Dirichlet conditions and the Neumann conditions, and these two remain largely the same. Okay, we'll keep it with a t naught and a g naught and a g1, a t naught and a t1, and a t naught and a t1. And again, you're going to be considering the wave equation on a finite line from 0 to L. Okay, good. So, okay, so the idea is going to be basically the same. You're going to do some algebraic manipulations of the wave equation in an effort to apply the boundary conditions. Okay, so you're going to take the wave equation and then you're going to multiply it by certain things and then integrate it. Before you do that, you're going to set up the problem and say, I have two distinct solutions, a u and a v, that satisfy the identical set of equations. And then you set your w to be u minus v, and you look at your w. You'd like to show that w is either 0 or non-zero. If w is identically 0, then u is equal to v, and there are no other solutions. If w is non-zero, or if there exist solutions where w is non-zero, then there may be other solutions. Okay? So you're going to let w be u minus v, and u and v are solutions of this system, either with this Dirichlet or that Neumann condition. And then you're going to verify that W will satisfy exactly the same set of equations. Okay, so I'll write that out here. W will satisfy WTT is equal to C squared WXX by linearity because U and V satisfy those equations. The difference here is that W of x and 0 is equal to U of x and 0 minus V of x and 0, and so F minus F. So you have 0 and then the same thing for the initial velocity. And then you have W satisfying the Dirichlet condition or the Neumann condition. Let's write down the Dirichlet condition. So you have 0 and T equal to 0 equal to W of L and T. Okay, because of course when you impose the boundary conditions on U, you have a T naught, and then you subtract the boundary condition on V, which is also a T naught because they both satisfy this set of equations. And so you have zeroed out the Dirichlet condition. If it's a Neumann problem, then you just zeroed out the Neumann condition that these two become WX's instead of W's. Okay? Again, by intuition, you expect that if this does satisfy a wave equation, right, then this is a string of length L that starts off with initial displacement of 0, initial velocity of 0, and with its edges being clamped at 0. So you would expect that the string would simply remain fixed for all time. And this is what you want to prove, that the trivial solution is the only solution. Okay? Remember as well that there's no gravity, so the string doesn't, it's just being held. There's no gravity, the string doesn't deform in the y direction. Okay, so what you're going to do is you're going to start off with this equation here and then multiply it by a WT and then integrate it over the domain. And then just do a little bit of calculus, and then it's going to get you there. So again, you're going to start off with a WTT is equal to a C squared WXX. And then you're going to multiply both sides of the equation by WT. Okay? This left-hand side, so let's just write here, multiply by WT. Multiply WT. This left-hand side you can rewrite as the derivative of a squared quantity, as you did in the heat equation case. So you can rewrite this as ddt of 1/2 WT squared. Okay? And then the right-hand side you just leave alone for now. Now the next thing you do is you just integrate both sides over the domain. And then you want to rewrite this using a product rule, okay? And so the product rule that you're going to apply is just the derivative of Wx times Wt. So I'm going to take the derivative. Let's note that if I take the derivative ddx of Wt Wx, then I have Wtx Wx plus Wt Wxx. Like that. Okay? Then I substitute this quantity here, Wt Wxx. Let's move this right-hand side term over to the left-hand side, and then substitute the new left-hand side into this quantity on the right here. Okay? So let's do it here on the same line. Move this over, then substitute this minus this quantity here. So you have a Wt Wx, Wtx Wx minus a ddx of WT WX. Here you get your brackets in there. Okay, now the next thing we want to do is we want to rewrite this term here as a time derivative. And the goal is for us then to move it over to the left-hand side and then combine with this time derivative. So let's note for this quantity here that you can rewrite this as ddt of 1/2 wx squared. And just make sure the 2 comes down, you have wx, wxt. Throughout all of this, you always assume that the functions are differentiable or sufficiently differentiable that the mixed partials are equal. So in this course, you don't worry about the inequality of the mixed partials. Okay, so let's move, once we've rewritten this as a derivative in time, we're going to move it to the left-hand side and then combine everything underneath the derivative sign. Notice here that this integration is in x. It's in the x variable of the w function. So you're free to move the time derivative outside of the integration sign. The integration isn't over the t. So we're going to move this over to the left-hand side and then move the time derivative out, and this becomes a ddt of an integral from 0 to L of 1/2 wt squared. This is a minus 1/2 c squared wx squared. Like this. And then just make sure, if I take the derivative, so this derivative of the first term gives you the term on the line above, and then this derivative of the second term returns this quantity here on the right. So then I'm left with a c squared, a minus c squared, and I can go ahead and integrate this term right away. So this is just the integral of the derivative, so you have a minus c squared times a wt wx, evaluated from 0 to L. Have I made a sign on the right-hand side? Was it because of this substitution here? Let me try to remember what happened. So I took the product rule. I took a ddx of this quantity here, wt, wx, that became a wtx, wx plus wt, wxx. That moved to the left-hand side. It became a negative. So I think if the chat can tell me if I'm right or wrong, but I think this is a plus and that's a minus. So if I change that to a plus and this to a minus. Good, thank you very much. Okay, so this changes this to a plus, and then this changes this to a plus. Okay, good. So now, you can also recognize this. If I was looking properly, I would have noticed that you can recognize this as 1/2 wt squared plus 1/2 c squared wx squared. This is the kinetic energy, right? 1/2 times velocity squared. Velocity is wt. And then this is the potential energy of the string. So you could have started on the left-hand side. If you were a physicist, you might start off almost immediately writing this as your potential and your kinetic energy, your kinetic and your potential energies. But in many ways, this is how the energies are derived, that you find these quantities which are special in the problem, and you can derive it just by algebraic manipulation, PDE. Okay, so we still have to deal with this right-hand side, and you get this right-hand side from the initial conditions. From the boundary conditions. So let me just be a little bit more specific here. If I have a Dirichlet boundary condition, so let me take, for example, w of 0 and t equal to 0. Okay, this is the Dirichlet boundary condition for the problem on the left. and you have the same condition for w of L and t. This is evaluated at x equal to 0, but you're free to take a time derivative of this, and you've not changed it, because you're taking the partial derivative with respect to a quantity which is not being evaluated. So if this is true, if w of 0t is equal to 0, then wt of 0 and t is equal to 0, because it's the partial derivative, and you're evaluating at x. That's fine. So in fact, this wt evaluated at 0 is 0, and similarly, wt of L and t is 0. So this is if you have the Dirichlet condition, okay? But if you have the Neumann condition, then the second term is 0. So if you have the Neumann condition, then Wx of 0 and t is 0, and Wx of L and t is 0. Okay? So either way, in both cases, this right-hand side is 0. So this goes away. And that's why I say as well that the mixed condition is a little bit harder. For the mixed condition, you have to go a little bit deeper into this right-hand side and figure out, if I know these things, then what can I do with the right-hand side? Okay? All right, so you're going to go and replace this now with 0. And in the context of the wave equation, it then makes sense for you to define this as the energy. This is your E of t. So you've shown that the derivative E prime of t is equal to 0. So you can think of this E of t, by the way, as an integral of the kinetic energy 1/2 mv squared plus the potential energy integrated over the string. Okay? That's the physical interpretation of what you're doing. In the context of the heat equation, you had a different expression for the energy. You had the heat energy. So, therefore, you concluded that dE dt is equal to 0. Notice I've changed it to a full derivative here, a full derivative because it's just a function of t, and the function of x is just integrated out. This is integrated into it for all time. Okay? So from that, you would conclude that the energy is constant for all t. Okay? But what do you know about the energy? If it's constant, can you figure out the value of that constant? Yes, you can, because you know that constant has to be 0. Because you know something about the initial energy of the problem. But the energy of 0 is just 1/2, it's just the integral from 0 to L of 1/2 W t squared of x and 0 plus c squared over 2 wx squared of x and 0. But you know by the initial condition, the version of this where it's 0 for both the f and the g for the w, that both these quantities are 0. So this has to be 0. So you know the energy is constant for all time, and you know it begins from 0. So you know it has to stay at 0 for all time. So therefore, the energy has to be identically 0 for all t. Okay? So now, the last thing is for you to show that W has to be identically 0. So you know that the energy has to be 0 for all t, so you know something about this quantity for all t. Now the energy has to be 0 for all t, And because the energy is expressed as the integral of a squared quantity, then the only way that's zero is if that entire integrand is zero. So if E is equal to 0 for all t, and since the energy is just the integral from 0 to L of 1/2 Wt squared plus C squared over 2 Wx squared, the only way that can happen, because these are squared quantities, is if Wt Wt squared is equal to 0 or Wt is equal to 0. For all t and for all x. Okay. Just be a bit careful with these types of conclusions. This wouldn't work if it was not a squared quantity, right? It only works because it's a squared quantity, because if you don't have a squared quantity, you can have negative area and positive area, which cancel out, and so you have the integral equal to 0, even though the functions are not equal to 0. But because they're squared quantities, you're integrating over the square of a function, you always have positive area for that. And so the only way this can be equal to 0 is if both of them individually are equal to 0. So Wt is equal to 0 and Wx is equal to 0, and you can come to the conclusion that W has to be equal to a constant. Okay? And then finally, the last step is for you to argue that constant has to be 0, but you know many things. You know that W has to be 0 on the left or on the right, and you also know it has to start from 0. So that constant has to be 0. But by the initial condition and or the boundary conditions, the constant must be 0. So therefore, W has to be identically 0, so therefore, U has to be V, and you have unique solutions. Okay? Be a bit careful, because a lot of students actually bypass this last step. They kind of jump, they say, well, the energy is 0, therefore W has to be 0. You have to be careful with that. The energy is 0, therefore the derivatives of W are 0, therefore W is a constant, but you know something about that constant. You know that at certain points, that constant has to be 0, so it has to be 0 everywhere. Okay? But this leap here, make sure you don't miss out on it. Okay. Good. Now, there was a question in the chat about the right-hand side term becoming a potential energy on the left-hand side. I don't think there's much to say about that. So this term had previously appeared on the right-hand side. Let me just refresh your memory about that. There was a term on the right-hand side which looked something, if I remember correctly, it looked something like c squared, a minus c squared, WTX, like this. And then this was rewritten as negative the integral of c squared dd dt of Wx squared. So just make sure if I take the time derivative of this Wx squared, I have that term above. And then this was moved over to the right-hand side, to the left-hand side, and now it gives you c squared Wx squared. Okay. This term here, many of you do recognize from maybe from A levels as a kinetic energy. This term here you might not recognize because you haven't learned it in your A levels or before university. This is the potential energy. Okay, so it makes sense the potential energy of a beam, for instance, will scale with the gradient squared. So the more you flex the beam, the higher the gradient, and so the higher the potential energy. Okay. Just out of curiosity, just out of interest, there are actually many ways for you to derive equations of motion. right? The way that you've learned in your physics courses or in your courses before university is the Newtonian way, where you say, well, I'm going to write down mass times acceleration. So I know Newton's laws. This is one of my fundamental assumptions. And I'm going to write down Newtonian laws and have mass times acceleration is equal to the sum of the forces. And from that, I can derive my equations of motion. This is what we did for the wave equation, right? We considered a small segment of the string. We wrote down mass times acceleration is equal to the sum of the forces. And then out came the wave equation. Out came that equation there. The other way to do it is, and you would learn it in other courses, is a sort of calculus of variations procedure, where you write down an energy for the system, you write down an integral over the beam or over the string that represents the energy, and you say that my string will be in a position in which that energy is minimized or maximized. And that turns out to give you the equations in motion as well. This is what's known as Lagrangian mechanics, or essentially Lagrangian mechanics. And these two ways of thinking about motion, or thinking about the laws of motion, one is Newtonian mechanics, mass times acceleration is equal to the sum of forces, and the other is Lagrangian, in which you say the motion will be such that some energy is minimized or maximized. These turn out to be equivalent. And so this way of thinking about energy by writing down integrals of certain quantities, a kinetic energy and a potential energy, may seem a bit unnatural to you because you've not seen it before, or you've not been presented this way of thinking, but actually it's one of the other ways of thinking about motion. Okay, so we've finished now the demonstration that the wave equation is unique. You'll notice that the only difference between the Dirichlet and the Neumann condition is how we treat that right-hand side term. And then in your problem sets, you're asked to look at the mixed condition. And in that case, you just have to do a few extra steps to manipulate this in a way that you can use it. Okay. You might wonder, well, in this case, we started off with the wave equation and then we multiplied it by a quantity, a derivative of time, a WT, and then integrated it. Whereas for the heat equation, you multiply it by a W and then you integrated it. And what's the trick to knowing what to do? Should I multiply it by a W or a WT? And I don't know the answer to that trick, right? These are essentially just tricks to put the equation into a form where you can express it as an integral of some quantity, and that quantity is identifiable with the energy. Okay, I don't know whether there is a general series of tricks you would do, but these are the tricks that we have accumulated for the heat equation, for the wave equation, and there's also one other equation, Poissons equation, which you're not at the moment expected to learn. Okay. All right. So now the very last part of this lecture, I'm going to cover how you do this in 3 dimensions. Okay. And the extension to 3D is the same. It requires the same basic tricks that you've been doing for the 1D. The only difference is that now you have to work, rather than integrating both sides over a line, you have to integrate over a volume or over a space. Okay? So let's do the example. Let me just see which version I want to do. Okay, let's do, just because we're already doing it, let's do the wave equation. So we're going to replace this wave equation with the version in the 3-dimensional version of it. And we're going to see, well, how is it different? Try and prove uniqueness. Okay, so we first replace this as, rather than the wave equation over a line, we replace it with a wave equation in general over a volume. And the difference there is that instead of the right-hand side being a WXX, it's now a Laplacian of W. So you have a UTT is equal to a C squared Laplacian of U, like that. Okay? The next thing is we're going to replace the initial condition and the initial velocity. And instead of an initial condition, in which U is equal to F over the length of the interval from 0 to L, you're going to require that I'm going to specify the initial condition on the I'm going to specify the initial condition on the object that I'm interested in. Here, so let me just hold on. Erase this, and I'll erase the mixed condition as well. And I just want to make sure that we'll go with the version of the problem that's done, the problem sets that we get. So you can just extend it right away. So the initial condition that we'll consider is still at time t is equal to 0, but instead we have to work with a vector x because you have an x, y, and z. And I'm going to say this is equal to some f of x here, where x is an element of the volume. Okay? And then finally, I have an initial velocity to deal with a ut of x and 0. And I'm going to say this is a g of x, where x is an element of the volume. So previously, x was from 0 to L. And then we have a Dirichlet or a Neumann condition to deal with. And for now, let's just do the Dirichlet version of the problem. Okay, so the Dirichlet version is that D is that u is equal to 0, u of x and t is equal to a constant. Let me make this to be, I can make it a constant, but I'm free to just do f of x. I'll make it up. Okay. So you could take the version where this is equal to a constant, but you might as well just make it a general function. And now x is an element of the boundary of V. Okay? In the one-dimensional case, let me just remind you, in the one-dimensional case, you had a string. All right, let's just draw the string. You gave an initial displacement of the string and an initial velocity of the string, and then you specified the string's value on the boundary. And in that case, the boundary were these 2 points, 0 and L. Okay? For the higher dimensional version, so the 3D version or the 2D version, let's imagine the version where you have a disk. This is the volume, and you're looking at the deflections of that disk. So it's like a drum. Okay, so you hit the drum. There's a deflection. I have trouble drawing the deflection, but it's the height of that drum. So again, you're going to specify initial displacement of the drum, an initial velocity of the drum, and a boundary condition. And the boundary condition is, in this picture, imposed on the boundary. Okay? So that's the only difference. Previously, the boundary were 2 points. In this case, it's a circle, and you might have something more complicated if you're looking to extend this to higher dimensions. The version of the Neumann problem is the same. The only difference is that rather than specifying the value of the function u, you're going to specify the normal derivative of the function u. But refer to the problem set to see the exact problem formulation. Okay? Just to be clear, it's to come up in the chat, my analogy with the drum was two-dimensional. It's two-dimensional, there's an x and a y, and then the deflection is given by the u. Okay, so this is the two-dimensional drum. I have an x and a y on the disk, and then the displacement of the drum is in the u direction. Okay? You can also imagine three-dimensional solid. You're looking at the vibrations of a three-dimensional solid. But that's more difficult to imagine. Okay, good. So you're going to begin with ut is equal to this equation here, or rather you're going to oppose a w, which will be the difference between the u and the v, and then you're going to work with the wave equation, multiply it by something, integrate over something, and then just manipulate things, and eventually you'll get to the same conclusions we had for the one-dimensional version. We could have proved everything, by the way, in this general framework. Without doing it in 1D, we could have just done it right away for 2D or 3D in higher dimensions with these Laplacian operators, and that would have been another way that we could have taught the course. So you're going to let your W of xt, and now x is a vector, be your u of xt minus v of xt, and u and v are distinct solutions, or u and v are solutions of this system. Okay, and then you're going to start off with the. Then you're going to conclude that wt then satisfies the same equation. Wt t is equal to c squared Laplacian w, but the difference is that w will have zeros for all the right-hand sides. So w starts off at 0. It has a time derivative, initial velocity, which is 0, and then it's set to 0 at the boundaries. So I'll be a little bit more specific with my domain. I've got the wave equation in V. I've got the initial condition and the initial velocity, the initial displacement and the initial velocity, in V being both 0. And then I'm going to have an initial displacement of 0 on the boundary. That's your Dirichlet condition. Okay? Then you're going to start off with this PDE. You're going to multiply it by a WT and then just integrate it. All right, let's go. So you've got your WT, T, is equal to a C squared WXX. And I'll just leave plenty of space here so I can do all my manipulations. I'm going to multiply it by a WT, as I did before. And then you'll remember the next step. Well, the next step was for us to rewrite this as a time derivative. But then it was to integrate over the domain, integrate over the line in the case of 1D. In this case, you're just going to do a triple integral. If you're integrating, if you're doing a three-dimensional version of the problem, you'll do a triple integral. If it's a two-dimensional, it's just a double integral. Okay, but let's do the triple integral version over the volume. Like that. This is also one of the reasons why sometimes in the course you don't want to specify the number of integral signs. You just write a single integral dv just so that it's more general. Thank you. Thank you. So there was a mistake here. I wrote WXX. I forgot to convert it to a Laplacian. Okay. So the next thing you're going to do is rewrite this right-hand side as a time derivative. Okay, so this becomes a ddt of the 1/2 WT squared dv. And then you'll notice that the right-hand side, previously what you did was you used the product rule to help you simplify this. Okay, so that's what we want to do now. So the product rule that you need is slightly different in this case. So you remember that previously we had ddx of wt wx. That was the product rule that we considered. Okay. In this case, I'm going to write down a product rule of, I don't quite remember what I need, so I'm going to just try it. I thought I need wt times, I'm going to see whether this gets me into any trouble here. So let's see. So this is going to get me a no, I want to do this version. Let me try again here. Okay, if I do that, does that get me what I need? So that gets me on the right-hand side. I think I do want this to be a WT. I do want that. Just because the WT, you move that to the left-hand side, you have a WT, which is then changed into, okay, I think you want that to be a WT, and you want that to be a WT, and you want that to be a WT. I think that's going to be our strategy. So we've written down a product rule, which essentially gets us one of the terms of the product rule is the term that we need on the right-hand side here. Then we'll move this to the left-hand side, then substitute it into here. And I think that should get us what we need. Let's try. So we have a triple integral of a ddt of 1/2 wt squared dv c squared. Triple integral, we'll have one term which looks like this, and then the negative of this term. So this is a term that looks like that, and then you'll move this over to the left-hand side. There's a negative. There we are. Okay. Yes, I think this will get us there. Okay. If you're ever confused, you do it in 1D first, and then you just see what the technique is in higher dimensions. Okay. So now I'm gonna end up rewriting this one here as a time derivative, and then you see it's gonna be the potential energy. It's gonna move over to the left-hand side and then become the potential energy. Previously, just the 1D version of this term here was a wx, you see, and then you rewrote it as a ddt of a wx squared. What about this one? What was this previously? Well, previously this was a ddx of wtwx, and then you just integrated it directly. And you can't do that anymore. You can't just integrate things directly because you have a triple integral. But what you can do is you can use the divergence theorem. Okay? So we're going to rewrite this one here. So let's note that ddt of this is equal to of 1/2. That is precisely that. So this is that. Okay? This is the same as it works in 1D. 1/2 ddt wx squared is equal to wx wxt. Okay? Once you've done that with this term here, you'll move it over to the left-hand side, and it becomes exactly the potential energy plus the kinetic energy. By the way, if you find this a little bit too fast, this is actually one of the problem set questions. Okay, so we're going to go through this here, and then you could duplicate it for your problem sets, and then just make sure you understand it well when you redo it. So this becomes a triple integral of a ddt 1/2 wt squared, which we've written there, and then you'll move this over to the right-hand side. It becomes a c squared Okay, it becomes a c squared grad w dot grad w, and grad w dot grad w is just the magnitude of w squared, like that. So go ahead and replace this with c squared. I forgot a factor of 2, magnitude of dw squared. And I'm missing a dv here, which I don't have space to write. Okay. Finally, you're going to convert this via the divergence theorem. So by the divergence theorem, you know that the triple integral of the divergence of f dv is equal to the double integral over the surface of f dot n ds. Okay? This is the divergence of a quantity. So this is your f here. It's going to be f dot n, this quantity dot n. So you change this to a surface integral, and this becomes this quantity dot n. I completely forgot the quantity. What was the quantity again? It was a Laplacian, yeah. What was the quantity? It was this, WT grad W. Silly. There we are. Okay. Okay, almost there, I promise. This becomes a c squared. Double integral. Let's rewrite this. I know that grad W dot n is just WT dW dn. This is just notation. And that's it. You're almost there. Now you know something about the value of W on the boundary. You know that W is equal to 0 on the boundary, so the time derivative of W has to be 0 on the boundary. So this whole term, in fact, is equal to 0. This is W squared, dW dn, ds. But W is equal to 0 on the boundary. And so therefore WT is equal to 0 on the boundary. For the same reasons we pointed out before, you just take the partial derivative with the thing that you're not evaluating, you're fine to do that. So this is, I don't know why I wrote that, this is a WT dW dn ds. So this term here is equal to 0. And at last, you've reconnected with what you did before. This is the time derivative, ddt. Go ahead and write ddt. Of the energy, 1/2 Wt squared plus c squared over 2 grad W squared dV is equal to 0. Previously, you had a 1/2 Wt squared plus a c squared over 2 Wx squared. Now it's a magnitude of the gradient of W squared. Okay? But then the conclusions are all the same from this step onwards. You know that the change in the energy has to be 0. Therefore, the energy has to be constant. If the energy is constant, then it has to be equal to its initial value. But you know the initial value of energy is 0. Therefore, you know something about the integrand, and that will tell you that W has to be identically 0. So therefore, E prime of t is 0, where E prime is this quantity here. Therefore, E of t is constant. But I know that E of 0 is 0, because if I evaluate this using the initial conditions, in which W is 0 for both the derivative and the function itself, then I would conclude now that the E of t is equal to 0 for all t. And then finally, this tells you that Wx, Wt squared is equal to 0, and the magnitude of W squared is equal to 0. And the only way this can happen is if W is equal to a constant for all t greater than 0. What constant does it have to be? Well, it has to be 0, because you know that it's 0 on the boundaries. By the initial condition, or the boundary condition, or the initial condition, W is 0. Okay? So you see that actually even though the manipulations are a little bit more difficult, right? As long as you understand the basic methodology, it's all the same. You start off the wave equation, WTT is equal to c squared. Before you had a WXX, now you have a Laplacian of W. You multiply by something and integrate it over the volume. Then you use a product rule to rewrite that right-hand side. You move one term over to the left-hand side, and now on the left-hand side you have a ddt of a kinetic energy plus a potential energy. And on the right-hand side, that's the main difference between 1 dimensions and higher. Previously, for 1 dimensions, on the right-hand side, you had the integral from 0 to L of a straight ddx of a quantity, dx. And then you integrated that quantity, you just removed the derivative sign, and you found out that this quantity, evaluated at either 0 or L, was equal to 0, just straight from the boundary conditions. For 3D, the main difference is that this becomes a triple integral over the volume of a divergence. And so what you do is you just use the divergence theorem to convert that to a surface integral, but you know values of W on the surface. So that allows you to claim that that term is actually equal to 0. And then at that point, you've linked up the two analyses and they're both the same. Okay? And in 4D, someone's at off. 4D, higher D, it's once you have the divergence theorem, it works similarly. Okay? The derivation of the wave equation and the heat equation, the uniqueness properties of the wave equation and the heat equation, this is the problem set 10 part. Okay, so what I'd like you to do is I'd like you to do your problem set 10. And in problem set 10, basically, you're asked to do, let me show you in tabular form what you're asked to do. You have 3 equations to work with, and you're asked to show uniqueness or comment on uniqueness in the context of the 3 boundary conditions, okay? I'd like you to wait for me to make the announcement, but for now, if you're going to go and try to sit down today or this weekend to try to do it, I would suggest you work on the heat equation and the wave equation. And I'd like just to confirm that Poissons equation is not something that you should be examined about, so you don't have to do that. But it's not so much hard to do Poissons equation, okay? But heat equation and wave equation, we've just done the wave equation here. So we've shown that the solution of the Dirichlet problem with the wave equation is unique in 3D, or in higher D than 1D. We also did it in 1D, so I'll do 1 arrow, 1 check mark for the 1D, and 1 check mark for the higher dimensional version. Yesterday, we did the Dirichlet condition for the heat equation and also the 1D version for the Neumann condition of the heat equation. And today we also did the 1-dimensional version of the wave equation. The Neumann version of the one that we just did, by the way, is not so much harder, and you already had it. You had an integral over the surface of Wt dw dn. So in the Neumann case, this is 0, and you have the same conclusions that you had. Okay. But what I'd like you to do is I'd like you to finish up those other cases for these 2 problems, the 1-dimensional case and the 3-dimensional or the higher dimensional case, and be comfortable just proving it, right? So once you understand the basic steps, it's easy for you to rattle off those types of proofs. Okay. And so we're going to end the lecture here today, having done the wave equation. And then next week, Tuesday, Thursday, and Friday, our plan is to get through, to make some final comments about this problem set number 10, and then to get through the massive music chapter in chapter 13, and then also to make a comment on the study guide and what plans you should have for preparing for the assessment. Okay. Otherwise, just going to wish you a good Friday, and I'll see you all next week.